three-way partitioning, except that it's not going to be as straightforward as Lomoto's partitioning, which is why I don't personally prefer Hoare's partitioning. Let's think about it. Now I have the Dutch national flag problem. I want, what do I want? Blue on the left? No, red on the left. Red, white, and blue. I want red, white, and blue. So I look at the leftmost number. I'm deciding to do some work up front instead of waiting till the end. I look at the first number. Maybe it's red, or maybe it's white, or maybe it's blue. If it's blue, I can send it to the right end, just like I did with the Polish national flag problem. But if it's red or white, it will need to stay on the left. Now the problem is there are two regions here on the left, red and white. So the general subproblem that we would face is something like this. This is a blank rectangle in the middle. There is a blue region on the right. There is a red region on the right, followed by a yellow region on the right. Red region on the left, followed by a yellow region on the left. And let's say we are 2 or 3 pointers have the same meaning. So what do I do when I look at the leftmost number here? If it's white, that's the best case. I just have to increment the white pointer. If it's red, I have to send it to the left. So I'll basically do what I was doing with Lomoto's partitioning for two colors. And if it's blue, I send it here. And just like the way we did it in, the two color version of this same strategy. So that's how I could write the code. So as long as the rectangle in the middle is non-empty, that means as long as blue minus white is not yet 1, I look at the leftmost number, which is array of white plus 1, and I decide if it is equal to white, that's the best case. I just increment the white pointer. Otherwise, if it is equal to red, right? If it's red, I need to do what I was doing earlier, which is to increment the red pointer forward and then swap the white and the red values. Now, actually, the white pointer also needs to move forward, right? Because the white index is not exactly, it's not a for loop, it's a while loop here. So if you visualize in terms of these pointers, you know what to swap. You need to swap so move the white pointer forward, move the red pointer forward, and then swap them. That would restore the order. Right, move the white pointer forward, move the red pointer forward, and then swap these two values. Right, swap the two values at the white and red indices. Okay, that makes sense, hopefully. What if it's blue? So suppose this is the region already. This of course will be red now. Now what if array of white plus 1 is blue? Well, we're going to send it, because this value is blue, so we'll send it here. So we do blue minus 1. Oops. Blue minus minus. And then swap with area of blue. In each of the three cases, our empty rectangle in the middle is shrinking by 1. So where do our pointers start out? When the entire rectangle is empty, these red and white pointers are sitting just outside the array on the left. So I would say red is at -1 and white is also at -1. And our blue pointer is sitting just outside the array on the right side. So our blue value will be the length of the array, right? The index that is just after n-1, just outside the bounds of the array. So this also is the way to, extrapolate, if you like, Hoare's partitioning to three-way partitioning. But as you see, these two are still being done similar to Romuto's partitioning. So might as well use Romuto's partitioning, although both can be looked upon as, variants of decrease and conquer. One in which we either do the work at the end, the other involves doing some work up front.
Uh, excuse me. In the last, where you have decremented blue pointer and swap them, the array of white plus one and blue. So the white pointer shouldn't be incremented, right? Because it's
Yeah, it's not incremented.
because
It's
we
not
have
incremented.
now added one more white element to the white part.
No.
So
We don't know. So what we did is we decided that we saw that this is blue, and
right,
so this needs to go here.
but you have decremented blue by one, which is now pointing to white.
So it's going to point here. The blue pointer will point to the
Point
leftmost
there,
blue number.
which is like blue pointer. It is already at leftmost blue, right?
Yeah, but now we have
But
one more. We have one more blue number now,
yeah,
extending that region on the right by 1. Right. The blue region on the right keeps growing in
right.
the left
But
direction.
right, previously it might have been white when you decremented it. Then the leftmost blue pointer was pointing to white region, and white plus one was blue.
No, no,
When you
no. It
swap them,
can't be, because as soon as the difference between them becomes equal to 1, we exit.
difference between blue and white becomes
Because
equal to one.
when this rectangle shrinks to become like this, there's nothing to do, right? There's no subproblem left to solve. At this point, the white pointer is here, the blue pointer is here, leftmost blue number.
What? So okay, right. There is only one difference. But when you incremented the red part, then you did increment the white pointer.
Yeah.
So now
Because
you have swapped a blue and a white element,
not white.
and
I swapped it with white plus 1. White plus 1 is this black, this this blank element. I don't know what its color is.
okay.
Actually, I know its color. It's blue. That's why I swapped it with this whatever was there. But I don't know
Right.
what that new number is which is coming here. I don't know the
Okay.
color of that.
Okay. That is unknown. You don't know the color. That's why it is white is not
Yeah,
incremented.
yeah. But what happened is blue got decremented. So the size of the we are decreasing the
Right.
rectangle. We are squeezing it from either end here. So either we squeeze it from the left end by 1, or we squeeze it from the right, shrink it from the right end by 1.
So whatever was in the left of the leftmost blue pointer got swapped with blue, and then white stays where it is because we don't know
Yes.
what we swapped it with. So that's why white stays where it is.
Yeah. So in the next step, we will look at what that value is and then decide what to do with it. But uh, in case one and case two, we shrink the rectangle from the left end by one because the white pointer is incremented. In
Mm.
case three, the blue pointer is decremented, so we shrink the problem size by one from the right end. Shobit,
Okay.
Yeah, Omkar, is it fair to say the number of swaps in Lomoto and horse partitioning are same, or is it different?
um, number of swaps. It would depend on how you implement it because the way horse partitioning is described is when both pointers are pointing to something that shouldn't be there, then you swap them and then it's like they exchange and then both of them get satisfied with a single swap. So
Okay,
that's a little more, I would say, optimized than when we are thinking about in a decrease and conquer way. We're only focused on one number, right? We've focused
okay,
on just with a single swap sending that number to its right region.
okay,
So so it's not clear that there's no one single version of force partitioning, at least the way I'm describing it.
okay,
So the
okay.
number of swaps also would not be the
Same.
same in
Oh, okay,
both.
okay, fine.
But Lomoto's partitioning is um
So my
um,
point is like I don't think like anyone will focus on the number of swaps, right? Like I don't like that's all I think, right?
if you
I
want
just
to minimize the number of swaps, what do you think is the do you remember what algorithm is that? You attended the array floaters, right?
yes, but I
Cycle sort.
Yeah, cycle sort.
Sorted.
So
oh,
if the goal is actually to minimize the number of swaps,
oh,
because you remember how uh, we shrink the cycles in cycle sort when we do the swap,
oh, I see. Okay,
right? And there is no way to, like, if the cycle is of size 5, you need 4 swaps.
okay,
Can't do better than that to
okay,
reduce the cycles,
okay,
to deflate those cycles.
okay, okay. Thanks, guys.
Sudeep,
Yeah, Omkar. Actually, my question was maybe related to the one which we discussed. My
hmm,
question was, I have seen some problems. I think in lead code only where it's very similar to partitioning, even odd, or some three-way partitioning
hmm.
with minimum number of writes. So, so I have seen such questions. So, like, uh, is cycle sort the actual approach or the uh,
Cycle sort will sort minimum number of writes. Uh, can you show me, like, so these are the lead code problems which are not identical but very similar to the 4 problems we have. I
okay?
haven't seen that kind of restriction in them.
Sure. I'll ping you that number, lead code number. Uh, but I was thinking the number of writes essentially means number of swaps in other way, right? Because you're actually overwriting some of the array values.
Well, if you not really, because sorry, you're saying minimizing number of writes is
Yes.
the same as minimizing the number of swaps.
Yes.
Uh, Again, not necessary. Uh, Not necessary. Actually, if you go to cycle sort, that actually minimizes number of writes, because if
Yeah.
you look at a cycle of size 5, you can actually do it in a circular way.
Correct.
Pick the
Correct.
first, like a musical chairs, that kind of. pick the
Ah,
number, put it in the next slot, pick that number, put that in the next slot, and so you can do
correct.
like a 5-way circular ride. If you actually want to minimize the number of swaps, sorry, I think I made a mistake when I said cycle sort minimizes the number of swaps. It actually minimizes the number of writes, and if you want to minimize the number of swaps, that would be selection sort,
Selections.
because every number that is in its wrong place is brought to its correct place with exactly one swap,
Oh
Yeah,
yeah.
so
right, in
even
selection.
I started thinking in that direction, like the minimum number of writes should be the better approach should be cycle sort. But I attended your floater session where cycle sort has particular pattern, right? So when the numbers are in this range or that range, kind of problems
uh,
between
yes, but
0 to
yeah, so but the algorithm is generic. If you remember, it runs in quadratic time. It is generic, but it will run, it will be more expensive when you use it on a generic array.
so that means it is still valid
Yeah,
that the number of writes are minimum with the
yeah.
cycle sort. Okay, got. Okay, another quick question, if you don't mind.
Mhm.
In the previous question, you told we cannot use for loop, right? But any decrease and conquer, I know that each time I decrease it by one, so the number of iterations is definitely going to be n minus one.
Yeah. The complexity will be n minus one.
So what I
Even
meant
if
is
hmm,
you can still use for loop, but you can play with I
order
and
n.
j.
But yeah, so either you increment, so just like in two sum, either you increment the I pointer or decrement the j
J
pointer.
pointer, but you know for sure that there will be the loop runs for n minus one times.
Yeah. So the complexity will be order n.
Oh, yeah.
Narendra?
Yeah, Ankur. So this code, can you repeat the when it is equivalent to red
When it is
red pointer?
equivalent to red, 3-way partitioning.
Yeah, the la-
The code or the
the
walkthrough?
code, the last one that you wrote. Yeah, this one.
So when it's red, uh, what we are saying in that case is this value, the leftmost number of the empty rectangle is red. So in that case, what we want to do is to take this and put it there and bring this. So by swapping it with whatever number is there, and whatever number is there is white, so that white number will come here. So this will become white and this will become red. That's what we want. How do we do that? We move the red pointer forward and the white pointer forward, and we make the two numbers swap.
Okay.
So move the white pointer forward, the red pointer forward, and then swap them, swap the numbers.
Okay. Get it.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today